Linguistics is usually divided into several subfields: syntax, morphology, phonology, and semantics. Syntax is about the rules that govern whether a sentence is grammatical. Morphology is the process of how words form or change. Phonology is about how words sound and how people perceive those sounds. And semantics, what we're talking about today, is about what words and sentences mean. A famous example of a sentence that is grammatical but doesn't make sense is colorless green ideas sleep furiously. So let's talk about how a computer can figure out that crazy sentence doesn't make any sense. In this overview video, I'm going to discuss this as a 2x2 matrix. For the rows, I'm going to discuss sentence and discourse semantics versus word level or lexical semantics. For the columns, I'm going to talk about old school versus data-driven approaches. And of course, you build a sentence out of individual words, so the distinction here isn't perfect. And then there are the large neural language models that turn word representations into contextual representations that further blur this boundary. But for the moment, let's just stick to the simplified conception of the world of semantics. Okay, let's first talk about old school discourse level semantics. Much of the classical approach views this as converting natural language elements into predicates. For example, the classic question answering system Sherdlu, pictured here, takes a query as a natural language input, converts it into a logical form with predicates and operators, and then executes that logical system to see whether the logical expression is true or false. For example, you can ask it the question, is at least one of them narrower than the one which I told you to pick up, can be converted into a logical form. There exists an x such that x is in a box and the width of x is less than the width of y and y was picked up. Now this seems like a reasonable way to do it. You need to do reasoning to answer such a question, and logic is a sound way to answer questions. So what's not to like? The problem is that it's very difficult to create predicates that comprehensively cover the things that English talks about. Let's go back to my example. We have the predicate picked up. But what does that match in the sentence? It says, I told you to pick up, but maybe Sherdlu didn't pick it up despite being instructed to do so. Then the predicate doesn't make sense anymore. And then there's also implicit constraints on logical reasoning in conversation. Humans aren't as specific as they necessarily need to be to reach full logical specificity. And there are complicated social rules about how to resolve those ambiguities. So just like how we need probabilistic formalisms to deal with syntactic ambiguity, we need to have data-driven approaches that can take a bunch of training data and create probabilistic outputs with predicates that can more flexibly correspond to the words that we actually use. And as I record this in 2022, many people are using abstract meaning representations to do this. It was introduced in this paper where the authors are oddly in alphabetical order. The senior authors are in the middle bottom here. The output of AMR is a graph that looks like this for the sentence, the boy wants to go. It's focused on verbs and verb frames. Who did what to whom and with what. Now this paper argues that you can turn these AMR representations into a logical form. So for example, this graph becomes, there exists some W, B, and G. You have an instance of W of the frame want, and an instance of G of the frame go, and an instance of B of the noun boy. The argument 0 of W is B, the argument 1 of W is G, and the arg0 of G is B. So how is this any better than what we had before? First, this graph should remind you of dependency parses. We have edges that go between words, or things like words, with labels on them. So we can reuse a lot of the techniques that we developed for syntactic parsing for the syntactic parse, including many of the probabilistic analyses that help us be a little less brittle than the old school logical forms. Let's continue with our overview of old school semantics, but move to lexical semantics. Thus far, when we've been talking about a word, we've just been talking about it as a string, or an integer that maps to a string. But that's not really how we use words. Words actually mean something. How do we convey that meaning to a computer? And more importantly, there isn't a one-to-one mapping between a word and its possible meanings. In addition to meaning a home run in the game of baseball, Homer could be a homing pigeon, the author of the Odyssey, or fictional characters named Homer Simpson, from either Matt Groening or Dave the Locust. So how could we tell a computer what a word means, or all of the various options that a word can mean? The first thing that might come to mind is a good old paper dictionary. That's how humans often learn new words. And a paper dictionary often lists the meanings a word can take on. Just look at a word and read the definitions. And there are approaches that let you do just that. For example, the Lexical method lets you figure out the best sense of a word in a context through dictionary definition. Let's say that you had the sentence, I had a bagel and donut this morning. Does bagel in this context mean the tasty Toreto breakfast food or a score of 0 in a sports game? The Lexical algorithm takes the definitions of a sentence and says, two words have compatible meaning if there's an overlap between the definitions. So you can tell that the definition of a breakfast bagel is a better match in the sentence by looking at the definitions of bagel and donut. You can see that the breakfast definition of bagel has a lot of overlap with donut, another breakfast ring food made out of dough, and you can declare this meaning of bagel the winner. But there's an infinite loop here. To understand a word's meaning, we need to read a definition, but that requires us to know what the words in the definition mean. Could you create a dictionary that computers could use a little bit more directly? Probably the most famous example of this is Princeton's WordNet, which for many years was housed in this building on Nassau Street in Princeton, New Jersey. George Miller and Christiane Feldbaum were the driving force behind this project, which aimed to create a network of words, hence the name WordNet. So cult is a concept in WordNet. It's defined by its relationships. It is a young horse, a foal, and it is also a male animal. So it inherits the properties of those two concepts together. And cult, the string, the word type, has two different meanings. So thus, cult is going to appear in two different places in the WordNet graph. Colt is also a type of handgun in addition to being a horse, but this instance of the word colt has a very different path in the tree. And the neat thing about WordNet is that, at least for the nouns, it's a completely connected graph. I have a lot of edges and nodes left out here, but everything is connected to the entity root node. WordNet has many different kinds of relationships, encoding antonyms, derivations, meronyms, and instance of relationships. This can tell you that George Washington is an instance of a president, that a hand is part of an arm, and that hot is the opposite of cold. And based on this network of relationships, you can define similarity relationships to tell you how similar words are. The closer they are in the network, and the more similar their paths are, the more similar the meaning. And this is easier than trying to get a computer to read definitions. But despite the decades of Herculean effort that went into constructing WordNet, the go-to tool for lexical semantics today is continuous word representations. Well, one problem is that continuous representations are data-driven, while WordNet is based on the expert knowledge of lexicographers. Representations, in contrast, reflect how a word is actually used in the wild. WordNet is slow. When a new word or a new sentence is created, it can take years for that change to be reflected in WordNet. But I think the most important distinction is that WordNet is discrete. While some senses are really completely different, like the cult example that we saw earlier, other meanings are more fluid. Here are three senses of the verb break. If I'm holding a pencil in my hand and writing with it, and I say that it broke, which sense really applies here? Maybe all of them? It stopped working, it fell to pieces, and it was overused. Training a machine learning system to match human judgments of senses with this inventory of some of the many possible definitions of break is really difficult. But WordNet is still useful and worth knowing about. If you need a list of everything that's a dog, easy to get from WordNet. If you want things that are a dog and an occupation, that's easy too. And while she was at Princeton, Li Feifei created ImageNet based on the architecture of nouns in WordNet. This is a fundamental resource in computer vision. And our next topic likewise led to a paradigm shift for natural language processing, moving away from discrete representations of the meaning of words to continuous representations of meaning, representing meaning with approaches like word2vec, which we'll talk about next. This is just one video from a course that I'm teaching. If you want to get the whole context, check out the course webpage, linked below. There you can find all of the videos in the right order. YouTube likes to show you older videos out of order, homeworks, exercises, and recommended readings. And if you want to help other people find videos like this, please be sure to like and subscribe to provide a big gradient to the algorithm.